Hello and welcome to this next lecture in pattern recognition. We'll continue with the support vector machine method. We saw last class the basic support vector classifier for two class case, and we have also looked at the kernel functions. This class will look at how to pose the regression problem also in the same way. So, we derive a support vector regression algorithm also, and then discuss a few issues about how actually we will solve for the support vector machine. Okay. So, just to briefly recapitulate, we have been discussing the SVM method for learning classifiers. The basic idea of the SVM method is that we transform the feature space, that is we map the feature vectors into some other space and then learn a linear classifier in the new space. So, basic idea is what is a linear classifier in this new space would be a nonlinear classifier in the old space. So, we can actually learn a nonlinear classifier using techniques of learning a linear classifier. The kernel function allows us to do this mapping implicitly, and thus kernels give an elegant method to learn nonlinear classifiers. Right. So, essentially what is a nonlinear classifier in the original space could be a linear classifier in the transform space, and the kernel functions allow us to do this mapping implicitly. So, kernels give us a elegant way to learn nonlinear classifiers. Okay. The same idea can be used in regression and many other problems. So, let us basically recapitulate what the kernel trick is. Okay. The kernel trick is, if originally the feature space is m dimensional, let us say Rm, we are mapping the feature vectors from Rm into some other space, I call it H. It could be Rm prime most of the time, but let us just call it H, which is some appropriate high dimensional space, a vector space in which there is an inner product defined. What the kernel function allows us is to compute inner products in the space H. So, if I have two vectors in Rm, say x and x prime, I want to calculate the inner product between phi x and phi x prime. I want to calculate phi x transpose phi x prime, that is an inner product in H. I can compute them as a function of just x and x prime. So, kernel function allows us to compute these inner products implicitly without using phi or without even knowing what the phi is. Right. Given x and x prime, I can derive a function of x and x prime, which happens to be the inner product of phi x and phi x prime. So, kernels allow us to do the computation of inner product in the H space implicitly and with no knowledge of the function phi. So, what it means is, by use of kernel functions, many algorithms that essentially use only inner products can be implicitly executed in a high dimensional space. For example, if I look at Fisher linear discriminant, right, the discriminant, which is W transpose X, as well as the way I learn it, right, using generalized eigenvalue problem, all of them only use inner products. So, I can actually, if I think of Fisher linear discriminant as finding a linear transform onto one dimensional space where I get the best separation between classes, I can ask, can I find the nonlinear transform, right. So, I can have a kernel Fisher discriminant and so on. So, any algorithm that uses essentially inner products can be implicitly executed in a high dimensional space. That is the basic idea of the kernel trick. It can be used in Fisher discriminant, it can be used in regression, it can be used in many other similar algorithms. So, basically what it means is, using kernels, we can elegantly construct nonlinear versions of linear techniques. Okay. So, now we are going to look at this in the context of regression. So far we looked at it in the context of classification, now we will look at it in the context of regression. What is the regression problem? We are given training data x1, y1, x1, yn, n training samples, where each xi is in Rm, is like our feature vector. Only thing, the targets now y1, yi are not plus 1 minus 1, but they are real value targets. Right. So, given this training data, we want to learn the best function to predict y given an x. We want to learn a function f such that y hat is equal to f of x is a very good prediction for y. Right. As we have seen earlier, essentially we can construct such functions in a parameterized manner as w1 phi 1 x, w2 phi 2 x up to wm prime phi m prime x plus b, where m prime is some arbitrary number. Let us write this phi 1 phi 2 phi m prime at the vector capital phi and the rest of it as w. So, I can write as w transpose phi x plus b. With a bit of abuse of notation, I am putting the parameterization on the left hand side only as w, even though w can, as we already seen, we can put b inside or outside depending on our convenience. So, even though I have a b here, I am thinking of the parameterization as w. Okay. That minor point apart, this is what we have seen when we use the linear least squares regression. We said as long as the functions phi 1, phi 2, phi m prime are fixed, this is like linear regression. I can always fix some functions. I have to choose what the functions would be and I have to choose what m prime would be, then I can do this. Okay. So, phi's are, as in general, R m 2 R functions. Now, essentially if phi I x is equal to x I, that will give me w 1 x 1 plus w 2 x 2 so on, of course, which will mean m prime is equal to m, then it is a linear model. That is simply w transpose x plus b, right. In general, of course, we seen this as a generalized linear model earlier, but now we can think of this as, if I think of phi 1 phi m prime, phi 1 x, phi 2 x, phi m prime x as an m prime dimensional vector, represent that as capital phi of x, which is a transformed version of x, right. So, I can think of z is equal to capital phi of x, which is in R m prime, and then we are essentially learning a linear model in the transform space. Right. This is basically the basic idea of SVMs. But even in our earlier least squares regression, we said if we fix the functions phi 1, phi 2, phi m, for example, we see how to learn polynomials in one variable simply as a linear regression problem, right. If I fix the functions phi 1, phi 2, phi m prime, it is no different from linear regression. The main thing that we want to gain now is, even if I choose the functions phi 1 to phi m prime, I have to work in the m prime dimensional space, right. I have to first transform all the x's to z's and then do a linear least squares regression in the z space. That is not what we want to do. We want to do this problem formulation in such a way that you can use the kernel idea. So, once again, it is the same kind of problem as in the classification case. So, I may have a 100 dimensional space in which I want to learn quadratic functions, but if I want to learn quadratic functions by explicitly specifying phi 1, phi 2, phi m prime, I will have 10,000 dimensional linear least squares regression problem. We do not want to do that. We want to use a kernel function, so that we do this implicitly. We do not even have to precisely specify the mapping phi, we only specify the function. Right. So, we want to formulate the problem in such a way that just like in the classification case, we will use the kernel trick. So, that we do not have to actually get into this m prime dimensional space, we do not have to suffer the computational complexity of calculating these phi's and solving a linear least squares problem in the m prime dimensional space. Okay. How do we do this? In any general regression problem, as you already seen, like in classification, we essentially minimize empirical loss, something like the empirical loss. So, if I am learning a model g x comma w, so L of y I comma g x I comma w is the loss, right. So, given an x I, I would say g x I comma w, the prediction that is given to me in the training data is y I. So, L of y I comma g x I w is the loss. So, I summed out all I, that is the empirical risk minimization, right. Of course, I can put a 1 by n in front, but that does not makes no difference. So, we have been doing so far by choosing an appropriate loss function, we essentially minimize an empirical risk like this. So, what we are going to do, as we have already discussed this in last class, we are going to use a special loss function that allows us to use the kernel trick. What is a special loss function? It is the epsilon insensitive loss function. We have seen this earlier when we did the formulation of risk minimization, empirical risk minimization, right. When we discuss loss functions, many different loss functions are listed and this is one of them. We also briefly discussed it last class. Anyway, so on an example x I y I for the model g x comma w, the loss will be 0 if y I minus g x I comma w absolute value is less than epsilon, otherwise it is absolute value minus epsilon. What does that mean? If the prediction is within epsilon of the true value, my prediction is g x I comma w, y I is the true value in the example. So, if prediction is within epsilon of the true value, then there is no loss. Epsilon of course, the parameter of the loss function, that is why I put epsilon as a subscript here. So, given a specific value of epsilon, if the prediction is within epsilon of the true value, there is no loss. Otherwise, the absolute value of the difference on over and above epsilon is the loss, right. Using absolute value of error rather than square of error, earlier we are not using any epsilon, we are just using square of the error and minimizing it. Using absolute value rather than the square of the error allows for better robustness, in the sense a few outliers do not give me, do not influence the final fit too much. Okay. But more importantly, the reason why you use this formula is that this particular loss function, when we want to do empirical risk minimization on this loss function, that gives rise to an optimization problem which has the right structure for us. For us, the right structure is one where I can employ the kernel function. Okay. All right. So, what is that I have to do? This is my model g x comma w, phi x transpose w plus b. Once again, w and b both are included in this w on the left hand side. Essentially, I have to learn w and b by minimizing the empirical risk. So, my empirical risk is for each example x I y I, my prediction is phi x I transpose w plus b, the two predictions is y I. So, I take the difference between them, absolute value of the difference minus epsilon. If that quantity is greater than 0, that is the loss. If that quantity is less than 0, loss is 0. So, this is my empirical risk, right. That is my epsilon insensitive loss function. If the difference is less than epsilon, the loss is 0, otherwise loss is this minus epsilon. So, loss is actually this minus epsilon comma 0, whichever is maximum, right. So, that is what I have to maximize. Okay. I can put 1 by n to make it actually empirical risk, I have to put 1 by n, but that does not really make any difference when I am minimizing this. So, this is what I want to minimize. What we are going to now do is we will write this unconstrained minimization into an equivalent constrained optimization problem, because that will allow us to get into the structure we want. So, this is what I want to minimize, right? Just remember this. So, basically given a w and b, ideally what I want either y I minus phi x I transpose w plus b less than epsilon, I mean which, or phi x I transpose w plus b minus phi less than epsilon, whichever is positive. Actually, I want both of them to be less than epsilon, because one of them will be negative. So, that is what I wrote here. So, the absolute value of this difference less than epsilon can be written as y I minus w transpose phi x I minus b. I want it to be less than epsilon. I want w transpose phi x I plus b minus phi I also to be less than epsilon. If one of them will be negative, so only one of these constraints is really useful. If that is less than epsilon, I am done. If it is not less than epsilon, I am using a slack variable j I. So, I need two sets of slack variables j I and j I prime. That tells me by how much the difference between y I and w transpose phi x I plus b differs from epsilon. Note that for any given I, only one of j I or j I prime is greater than 0, both cannot be greater than 0, right, because one of these left hand sides is negative, right? It really does not matter which one. So, but one of them is the operational one for any given I, right? And that j I prime tells me that j I or j I prime gives me the actual absolute value of y I minus w transpose phi x I minus b minus epsilon, right. So, essentially what we are saying is, say j I, one of j I or j I prime will be greater than or equal to absolute value of y I minus w transpose phi x I minus b minus epsilon, and is also greater than or equal to 0. So, if I just add these j I's, this j I and j I prime is nothing but max of this minus epsilon. Okay. So, I can always write such an unconstrained maximization problem as a constraint unconstrained minimization problem as a constrained minimization problem of this. So, of course, I am trying to find w, b, j and j prime, right, to minimize this while satisfying all this. Okay. This is a nice problem, but which exactly is same as minimizing this empirical risk, right, as A G to C, minimizing this empirical risk is equivalent to solving this constraint optimization problem. So, the problem is nice, but we have a problem. We have a problem in the sense this problem is nice, but it does not serve our purpose. This does not give a dual with the structure we want. So, we will slightly reformulate this. What do? We keep the constraint same, but add a half W transpose W, just like, so that it looks like, what we solve for the constraint. Why should I add this half W transpose W? Well, we will come back to that little later in today's class. I will explain you why we want to add half W transpose W. Right now, let us say, so if I had only this term, the constraints on this term, then it is exactly like minimizing the empirical risk, but I am adding this. So, what we can think of this is, along with these constraints, this is the empirical risk. So, this in some sense is like a model complexity. Okay. So, this is the data error, as you already seen, this term captures the empirical risk under the epsilon insensitive loss function. So, this is like some term which is model complexity. So, I can think of this as a regularized risk minimization. We already seen in linear least squares regression that we want to we may want to put a regularization term, so that we will learn a smooth model instead of completely putting all our attention in minimizing the data error, that is minimizing the empirical risk, and we only minimize the empirical risk, we may not learn as nice a function as if we also pay a little attention to the complexity of the model. There also we just mentioned that an often used model complexity term for linear models is the norm of W, right. So, the same norm of W we are using here as a regularization term. As I promised you, before the end of today's class, we will come back and ask why is this a good way to characterize the smoothness of the model we are learning. Okay. So, for now, we will simply say that earlier, if I did not have that W transpose W, that is exactly equal to the empirical risk. So, in addition to minimizing empirical risk, I add a model complexity term, so that this problem now corresponds to a regularized empirical risk minimization. Now, we are in business. This now is very easy to see, except that instead of one Ji, I have Ji and Ji prime. I essentially have similar kind of constraints and similar kind of problem structure as SVM. So, I would expect similar kind of things to happen. So, like earlier, we can form the Lagrangian, right. This is the objective function, these are constraints, form the Lagrangian, put in the counter conditions, right. That will give you the expressions for optimal values of W1B. Given the structural similarity, we will expect the optimal values of W1B to be similar to the earlier expression. So, it means we can write W star and B star in terms of the optimal Lagrange multipliers. What Lagrange multipliers? Essentially, the Lagrange multipliers corresponding to the inequality constraints on the errors. Just like there also, the Lagrange constraints and Ji's are not important to us. The constraint Ji greater than or equal to 0. The Lagrange multipliers correspond to those constraints are not important. Basically, the inequality constraint that on the errors in the data would be the determining factors, and we can always use the same technique as earlier, that is, we formulate the dual to solve this. Okay. Once again, this is as you can see a quadratic cost function, a convex cost function and linear constraints. So, you can use the same technique as you used earlier for deriving the dual using the dual function, and if you do all that, the dual turns out to be this. Okay. We will just omit the details because the derivation is quite similar. So, now we have two Lagrange multipliers, alpha and alpha prime, right. So, basically there are 4 constraints, okay. 1, 2, 3, 4. So, the constraints for this, let us say these are the Ji constraints, these are the Ji prime constraints. So, the Lagrange multipliers corresponding to Ji constraints are alpha I, Lagrange multipliers corresponding to Ji prime constraints are alpha I prime. These constraints are not important, just like in the SVM case, the Lagrange multipliers corresponding to these constraints will not enter into the dual. So, dual is in terms of alpha and alpha prime, right. We have alpha I is equal to 1 to n and alpha I prime I is equal to 1 to n. Those 2 n variables are the Lagrange multipliers corresponding to these 2 n constraints. So, that turns out to be the objective function, and these have turned out to be constraints. Once again, like earlier, all the Lagrange multipliers have to be between 0 and C, and there is one equality constraint, and then the objective function, the dual, is also quadratic in both alpha and alpha prime, and the training data themselves appear only as inner products phi xi transpose phi xg. So, all the structure that we had for the SVM dual still is there. The details don't really matter to us, the actual terms are different here compared to the SVM, but the overall structure is same. It is a quadratic cost function, one linear equality constraint, bound constraints and variables, and the bound is between 0 and C, where C is the same penalty constant, and the training data appear only as inner products in the objective function phi xi transpose phi xg. Using the Kunteker conditions as earlier, we can derive the optimal values of W and B, and it turns out to be the same. W star is sum alpha I star minus alpha I star prime phi xi. So, as I said, alpha i's are corresponding to the first constraint, alpha I primes are corresponding to the second constraint there. So, this happens to be the W star and B star. Okay. Let's look at these expressions. First, let us note certain things about this primal problem. As you already seen, only one of Jia and Jia prime is non-zero. The other, because on the LHS, one of these terms is negative. So, for any given I, only if at all, only one of these constraints can be exact. There will be only one Jia which is strictly greater than 0, right? Which means, because our Lagrange multipliers are alpha I here and alpha I prime here, the complementary slackness shows us that both alpha and alpha I prime cannot be simultaneously greater than 0. For them to be greater than equal to greater than 0, both inequalities have to be satisfied by equality. That is not possible. So, only one of alpha and alpha I prime are would be greater than 0 at the optimality point. And similarly, if suppose this is positive. So, y minus w times of phi xi minus b, if it is actually strictly less than epsilon, then Jia will be 0. So, once again, even among that particular, among the alpha is that only one of alpha and alpha I prime are greater than 0, as I said, for each I. In addition, not all alpha i's or alpha I primes will be. If I look at all the strictly greater than 0 Lagrange multipliers, they may not be one of them. They most probably will not be one of them, right? Like the support vectors in the classification case, basically only when this inequality has to be strictly satisfied, only that is, so that Jia is strictly greater than 0, only then the corresponding alpha I will be positive. Okay. So, which means we know by looking at the primal problem that only one of alpha and alpha I star prime is non-zero, and both of them will be 0 for examples where error is strictly less than epsilon. Okay. Now, when I with that in my mind, if I look at the W star, essentially W star is nothing but a linear combination of sum of your data phi xi and the coefficients are the Lagrange multipliers, because in this term it is either alpha I star or is minus alpha I star prime. So, coefficients are simply Lagrange multipliers. So, the final W is a linear combination of some of the examples. Which are these examples? The support vectors, wherever the corresponding Lagrange multiplier is strictly positive, right. And the dual and the final solution both are such that the kernel trick is feasible. The dual, as we already seen, the data phi xi appear only as inner products. So, I can use the kernel there, and the W star is a linear combination of phi xi. So, once again I can use the kernel trick, and the B star comes as phi x transpose W star. So, once again I can use the kernel trick, right. Specifically, suppose we have a kernel function, then what is my optimal model? G x comma W star is this is my expression for W, right. So, W transpose phi x plus B star. So, this can be kernelized, this can be as k x I x and B star, and B star can also be kernelized, because B star is phi x j transpose W star is linear in phi x. So, this term also involves only phi xj transpose phi xi. So, once again this can be canalized. Okay. So, this can be canalized, and as earlier B star can also be written in terms of the kernel function. So, the way we formulated the regression problem, let us go back to our formulation. This is how we formulate the regression problem. We put in this extra regulation constant, right, and otherwise it is like the SVM formulation, right. This is actually minimization of empirical risk under epsilon insensitive loss function along with a regularization constant, and for that problem that happens to be the dual. Dual has the very right structure, right, and with that dual, right, I get my solution in the right way, right. So, that the solution allows me the kernel trick. Specifically, I can write my final function like this, where B star can also be obtained through the kernels. Okay. So, essentially now I do not have to calculate phis, I only stay in the m dimensional space or the original space of the exercise and still learn nonlinear regression functions, right. So, once again the kernel trick allows us to learn nonlinear models using a linear method. For example, if we use Gaussian kernels, we get a Gaussian RBF net, right. So, if this is Gaussian, k exponential k x I x is exponential minus norm of x I minus x whole square, then this is nothing but linear combination of Gaussian real basis functions. So, this is actually the output of an RBF network, the standard RBF network, Gaussian RBF network with Gaussian real basis function hidden nodes and linear output node, right. So, the kernels automatically give you this. So, if you use a Gaussian kernel, we get a Gaussian RBF net just like in the SVM case, and just like in the SVM case, the RBF centers are easily learned here, they happen to be the support vectors. There are parameters, of course, any algorithm has parameters, right. We have the penalty constancy, which is like the regularization constant, epsilon, we would choose the epsilon insensitive loss function, and any parametric kernel function. For example, if I am using a Gaussian kernel, I may use a sigma, right. So, these parameters have to be chosen properly, but if I choose the parameters right, I get fairly good performance, and this basic idea of support vector regression is also used in many related problems. Okay. Basically, what happened was, by using the epsilon insensitive loss function, points whose targets are within epsilon of the prediction do not contribute to loss. That is what has given rise to the nice structure in the problem, and it also gives us some interesting thing like this, the support vectors. As we know, in the general classification problem, the support vectors are a very good byproduct. As we said, they represent all the patterns which are closest to the boundary between classes. So, and once we solve a problem and get all the support vectors, if from my training data set I remove all the things but the support vectors, I will still get the same SVM, because those are the closest to the training class boundary. So, if I can separate them, I will anyway separate the rest of them. So, the SVM on the entire training data will be same as the SVM rerun on the support vectors, right. So, essentially the same way the support vectors also represent the regression function too. So, for example, this epsilon, because the epsilon loss function, we can show that the local movement of target values of points outside the epsilon tube, that is the epsilon tube is like the W transpose x plus b is equal to plus 1 or minus 1, the two parallel hyperplanes in our classifier. Here, given our predictor function W transpose phi x, any prediction that is within epsilon of this does not contribute to any loss. So, I can put an epsilon tube around this prediction function, right, and we can show that if you move targets outside this, that does not much influence the regression. Okay. So, robustness comes through this support vector representation of the regression. Okay. All right. Now, let us get back to our regularization term, right. As I promised you, I said I will tell you why it is all right to add W transpose W, right. We chosen a epsilon insensitive loss function, we want to minimize the empirical susceptible loss function, and the rest of the formulation is fine except the term W transpose W, and we said it is like a model complexity term. Okay. So, basically this is my empirical risk I is equal to 1 to n max y I minus phi etc. W minus b minus epsilon 0. This is what is captured by summation j I plus summation j I prime subject to those constraints. In addition, I added this. So, this is essentially what I am minimizing. So, this is the empirical risk, this is the model complexity, and that is what I am minimizing. Okay. So, this is regularized risk minimization. The only thing we have to show is why is this a good regularization term, right. So, W transpose W is the model complexity term which is intended to favor learning of smooth models. Why do we use regularization? Why do we use the model complexity term? Just because I am minimizing my data error is not enough, as we discussed when we discussed statistical learning theory. We need to learn simpler models, right. The simpler the model, the better it is. So, essentially we want more smoother models. Okay. So, the W transpose W term is a complexity term which is intended to favor smoother models. So, we have to ask why is this a good term to capture degree of smoothness of a function being free. Smoothness is being nicely continuous. There are many continuities. A continuous function is kind of a continuity is a binary property. A function is either continuous or not continuous, but all continuous functions are not same. Right. Let us say f r m to r is a continuous function. What does continuity mean? I can make f x minus f x prime, the difference between f x and f x prime, as small as I want by taking the norm of the difference x minus x prime sufficiently small. But if f is even if f is continuous, if it is varying rapidly, then to make the difference between f x and f x prime small by the same epsilon, I may have to make the difference between x and x prime very small. So, for a given difference between f x and f x prime, how small should I have to make x minus x prime is a kind of one kind of measure to say how fastly or slowly varying the function is, and which is one measure of how smooth the function is, right. So, there are ways to characterize what can be called degree of continuity or degree of smoothness of function. We are going to look at just one such measure. Okay. We just look at one such measure, how to characterize the degree of continuity of function. The measure we will look at is what is known as an epsilon margin of a function. Given a function f r n to r and some epsilon greater than 0, for that epsilon, the epsilon margin of the function, we generally write as m epsilon of f, is infimum over all the numbers norm x minus x prime, so that f x minus f x prime is greater than 2 epsilon. We are saying, given an epsilon, I want to keep f x minus f x prime at least 2 epsilon, right. F x minus f x prime has to be large, so to say, right. F x minus f x prime has to be greater than 2 epsilon. I am asking of all x minus x prime that will allow f x minus f x prime to be greater than 2 epsilon, what is the smallest of that? Right. So, how small x and x and how close x and x prime be, still keeping f x minus f x prime large. Right. So, if m epsilon f is small, that means x and x prime, even very small difference between x and x prime can make f x minus f x prime large, then is not very good. On the other hand, if m epsilon f is large, then it is good. Right. The larger m epsilon f, the smoother is the function. M epsilon f, the epsilon margin being large means what? The smallest of norm x minus x prime, which ensures f x minus f x prime is greater than 2 epsilon, is still large. Right. So, even if I want to make f x minus f x prime more than 2 epsilon, I can still keep, I do not have to keep my x and x prime very close. Right. So, that is what the basic idea here is. Okay. So, the larger the epsilon margin, the smoother is the function. Now, it is easy to see that suppose f is discontinuous. If f is discontinuous, then epsilon margin will be 0, because around the discontinuity, at the point of discontinuity, no matter how small I make x minus x prime, this can still be greater than 2 epsilon, because fx minus fx prime is strictly greater than 0. So, there will be an epsilon, so that this is always greater than 2 epsilon, no matter how small I make x minus x prime. So, it is easy to see that the epsilon margin is 0 if the function is discontinuous. But interestingly, the epsilon margin can be 0 even if the function is continuous. If you look at the function 1 by x, obviously it is continuous, but as x comes closer to 0, it is varying faster and faster, right, because its rate of change is of the order 1 by x square. So, as x becomes closer to 0, it is varying faster and faster, right. So, it is not a really smooth function, because it varies very, very fast. So, there can be continuous functions like this, for which also epsilon margin is 0. One can show that for every epsilon greater than 0, if the epsilon margin has to be greater than 0, then f has to be uniformly continuous. Do not worry if you do not know what uniform continuity is, we really do not need it. Essentially, higher the margin, the smoother the function is, that the function is slowly varying and hence it is smoother. That is basically what this is, right. We have defined this at the epsilon margin, right, and it's easy to see that higher the epsilon margin, the smoother the function is. So, now let us calculate the epsilon margin for linear models. Okay. So, we have a linear model, then fx minus fx prime, because fx is w transpose x, fx minus fx prime, even if fx is w transpose x plus b, then fx minus fx prime will be w transpose x minus x prime, right. So, to find epsilon margin, what do you have to do? Given x and x prime, such that w transpose x minus x prime is greater than 2 epsilon, right. Find all x and x prime which satisfy w transpose into x minus x prime is greater than 2 epsilon. Among all such pairs, calculate norm x minus x prime and ask for which pair is norm x minus x prime smallest. That is what is infimum in the definition. So, we are asking, when would norm of x minus x prime be smallest if we have to make w transpose into x minus x prime greater than 2 epsilon. Firstly, the constraint is greater than 2 epsilon, because I want norm of x minus x prime to be smallest, and this inner product is nothing but norm w norm x minus x prime into some cos of angle, so to say. It is better to take it to be 2 epsilon, right. So, w transpose x minus x prime equal to 2 epsilon would be satisfied by x and x prime which have smaller norms, then w transpose x minus x prime is greater than 2 epsilon. And among all x and x prime that will satisfy w transpose x minus x prime equal to 2 epsilon, the one that will have the smallest norm is that pair, so that the vector x minus x prime is parallel to w, right. Here we know this is norm w norm x minus x prime into some factor which is less than 1. That factor becomes 1 if the two vectors are parallel. So, if the two vectors are not parallel, because that factor is less than 1, correspondingly the norm has to be larger. So, that is still 2 epsilon. So, the smallest, the pair x and x prime with the smallest norm x minus x prime, which still satisfies this, is such that w transpose x minus x prime is equal to 2 epsilon and the vector x minus x prime is parallel to w. What does that mean? X minus x prime should be parallel to w. So, it should be k times w, and w transpose x minus x prime should be 2 epsilon. So, if it is k times w transpose w should be equal to 2 epsilon. There is an absolute value. So, k can be only plus minus 2 epsilon by w transpose w. So, x minus x prime is either plus 2 epsilon by w transpose w into w or minus of that. So, my epsilon margin is nothing but the norm of this smallest x minus x prime. If I take norm of this, that will be 2 epsilon by w transpose w into root of w transpose w. So, that will give me 2 epsilon by norm w. So, for linear models, the epsilon margin is nothing but 2 epsilon by norm w. This is what we call the margin of the hyperplane in the classifier, right. So, essentially, when I added a term to minimize norm w, I am promoting learning of the smooth. So, for all linear models, because the epsilon margin of the function is inversely proportional to norm w or norm w square is a good regulation term to add, right. We have done it in regularize the least squares also earlier without explaining. Here is the reason why norm W square is a good regularization term. Okay. So, this completes our discussion on regression. Okay. So far we looked at support vector machines for classification and regression, but in both cases we just said solve the dual. We never said how do I solve the dual. Dual is a constraint optimization problem. We are not really given any algorithm for solving the dual, right. We have to solve a constraint optimization problem to obtain the Lagrange multipliers, and once you get the Lagrange multipliers you can get the SVM. So, there is one optimization problem, namely the dual which is a quadratic programming problem, which needs to be solved. We have not looked at any algorithm so far for this. This dual has many some interesting structure. So, there are many specialized algorithms proposed for this. Okay. So, this is the dual. Let's remember this is the dual. We want to maximize our mu, some objective function which I call q mu, which is equal to summation I is equal to 1 to n mu I minus half mu I mu j y I y j k x I x j. This is like a quadratic form of the k x I x j's. Okay. So, if I got x1 to xn are the data vectors and I make a matrix whose ijth element is k x I x j, mu I mu j k x I x j is nothing but the quadratic form of that matrix with respect to the vectors mu the vector mu, and we have to also of course multiply this matrix by y I y j. The ijth element has to multiply by either plus 1 or minus 1. Remember y I and y j are plus 1 minus 1. So, the product is either plus or minus depending on whether both x I and x j in the same class or different classes. Okay. So, this is essentially a quadratic form. So, this is a quadratic cost function subject to one linear inequality constraint and bound constraints and variables. It is a quadratic programming problem with very interesting structure, and hence there are many specialized algorithms. So, we will not consider any algorithm in detail, I will just mention where the specialized algorithms come from, but before going there we will solve one trivially simple problem just to get a feel for how one solves for an SVM. So, we will first consider a very simple example in R2. Let us say only 3 examples in R2, minus 1 0, 1 0, 0 0. Minus 1 0 and 1 0 are in class plus 1, 0 0 in class minus. Matter of fact, they are all of them are y component 0. So, it is actually a one dimensional problem. So, we call it 2 dimensional problem. Okay. So, it is a very simple thing. For all that it is simple, a linear classifier is still not sufficient, right, because see this is my problem. So, this is one class, the 2 reds or 2 stars are in the same class and the center circle is a different class. So, this is not linearly separable, they are in a line, as we already seen 3 points which are collinear cannot be shattered, right, by hyperplanes. The middle point is one class. So, I have chosen that. So, middle point is one class, the outer 2 are the class. So, for all that is a very simple 3 point thing, it is still not solvable by linear classifier. So, let us say we choose a kernel function of this kind, which essentially gives a second degree polynomial in the original space. So, this is my thing. For example, I know one classifier is this, right. I just put now the origin at that 0 0 thing just to once again see. So, basically if I have some line parallel to y axis on either side. So, the thing in between the lines is one class, outside the lines is other class. So, it is like a pair of lines kind of a classifier. So, essentially if I square the x coordinate, then these two will become same, right. So, I can actually get a threshold on the x coordinate square as a classifier. So, it is a quadratic classifier. But of course, we know this, but my SVM has to automatically find, instead of I just choose a kernel function and go ahead and solve for the SVM. So, how do I solve for the SVM? I need to know the to write the dual has k x I x j in it. So, let us first calculate k x I x j. K x I x j is 1 plus x I transpose x j whole square. We can write that as a matrix notation. These are the x's. So, 1 plus x 1 transpose x 1 whole square, x 1 transpose x 1 is 1. So, 1 plus 1 is 2, 2 square is 4. X 1 transpose x 2 is 0, sorry, is minus 1. So, minus 1 plus 1 is 0. So, k 1 plus x 1 transpose x 2 is 0. X 1 transpose x 3 is 1 is 0. So, this becomes 1. And similarly, for x2 transpose x2 is once again 1. So, the kernel function is 4 and x2 transpose x3 is 0. So, the kernel function is 1 and finally, x3 transpose x3 is 0. So, this kernel function is 1. Right. By the way, this obviously, this is a symmetric matrix. Okay. So, what will be my dual now? My dual is q mu, the objective function is I is equal to 1 to 3 mu I plus the quadratic form on this. So, 4 mu 1 square plus 4 mu 2 square plus mu 3 square. Then I have all the cross terms, mu 1 mu 2 has coefficient 0 goes away, mu 1 mu 3 is 2, mu 2 mu 3 is also 2, but both mu 1 mu 3 and mu 2 mu 3 will be minus terms because 1 and 3 are in different classes and 2 and 3 are also in different classes. So, it will be 4 mu 1 square, 4 mu 2 square, mu 3 square minus 2 mu 1 mu 3 minus 2 mu 2 mu 3. This is my objective function. What are my constraints? Mu I y I is equal to 0. So, that is mu 1 plus mu 2 minus mu 3. Mu 1 and mu 2 are in class plus y1 and y2 is plus 1, y3 is minus 1. So, mu 1 plus mu 2 minus mu 3 is equal to 0 and mu's are positive. Okay. This is my problem to be solved. Okay. What? So, let us form. So, this is the dual, but it does not really matter to us. This is just a constraint optimization problem with this as the objective function. These are the constraints. So, I can once again use Kuhn-Tucker conditions. So, to form the Lagrangian is this q mu plus Lagrange multiplier in constraint. I will have one Lagrange multiplier for this constraint, let us call that lambda. I have some 3 Lagrange multipliers, I have to write this constraint as minus mu I less than or equal to 0. So, ultimately I get that as my Lagrangian, q mu plus lambda into one constraint minus alpha I mu I, where alpha is are the 3 Lagrange multipliers for these 3 constraints. That is my Lagrangian. Now, to solve this using Kuhn-Tucker condition, what are the Kuhn-Tucker conditions I have? My optimization variables are mu 1, mu 2, mu 3. So, I can take partial derivatives of L with respect to mu 1, mu 2, mu 3 is equal to 0, that gives me 3 equations. I know mu's have to be feasible, so they have to satisfy all the constraints. So, mu 1 plus mu 2 minus mu 3 should be equal to 0, that is a constraint. So, that I get 4. So, this gives us 4 equations. How many unknowns I have? Mu 1, mu 2, mu 3, lambda and 3 alphas. I have got 7 unknowns. So, I need 3 more equations from somewhere. Where do you get the extra equations? I have to use the inequality constraints and we can use the complementary slackness on alpha is. What does complementary slackness alpha is say? Alpha is correspond to the constraints mu I greater than or equal to 0. So, the complementary slackness tells us that alpha I mu I is equal to 0, which means if mu I is strictly greater than 0, then alpha is 0, right. Otherwise, mu I is equal to 0. So, mu I is equal to 0, I do not need to know mu I, right. And if mu I is strictly greater than 0, alpha is equal to 0, I do not need to know alpha I. So, because the 3 complementary slacknesses, essentially they give me the remaining 3 equations. Essentially, in the sense, they will tell me which alpha is or mu is or 0, right. But I really do not know which are 0. I have to actually, in a general constraint optimization problem like this, I have to make a guesswork on which mu i's are greater than 0. So, that I can take the corresponding alpha to be 0 and solve this. What one normally does if you are solving a constraint optimization problem in pen and paper is to make these various guesses like this and then see which guess gives rise to a consistent solution. In SVMs in general, in this particular toy problem, but in SVMs in general, this is very simple to make because we know that mu I greater than 0 has a physical interpretation. If mu I is greater than 0, the corresponding xi is a support vector, that means it is closest to the separating boundary. So, I can actually geometrically think of which x's are at least in R2, I can do this, right. In this problem, of course, we know all the 3 are support vectors. So, we know that all mu I will be greater than 0. So, we can take all alpha I to be 0. That means, we have only 4 unknowns and we have got 4 equations. So, we can solve for it. So, if I put these 4 equations down, that will happen to be the 4 equations. Okay. It is easy enough to see. Essentially, I am differentiating this. If I differentiate this to mu, see when differentiate q mu, I get 1 from this with respect to any mu I and a mu term from this the square, and then the mu 2 and mu 3 term from the cross terms. Okay. And then from here I will get a lambda term, alphas are 0, right. So, roughly one can see that that the general structure of the equations. Okay. If they just happen to equations, you can differentiate and see. Now, and this particular case is chosen so the equations are very simple to solve. We already can see that say mu 1 plus mu 2 minus mu 3 is equal to 0. I got mu 1 plus mu 2 minus mu 3 here. If I put that equal to 0, I got lambda equal to 1. And looking at these two equations, if I subtract one from the other, I know mu 1 is equal to mu 2. And from here, I know mu 3 is equal to mu 1 plus mu 2. So, I know mu 3 is equal to 2, mu 1 is equal to 2 mu 2. So, mu 1 is equal to mu 2 and mu 3 is twice of that. Right. Once I put that in, it is absolutely straightforward to see that the solution is mu 1 is equal to mu 2 is equal to 1 and mu 3 is equal to 2. This completed in the SVM. That is all the SVM is. I have all the non-zero Lagrange multipliers and the corresponding support vectors. Right. Just one thing, I have not used the penalty constant in this formulation because it is a toy problem, but if I use the penalty constant with greater than 2, I would get the same solution, because using the penalty constant simply means that in the I have an extra constraint that says that all mu's have to be between 0 and 2. Even with unconstrained, my mu's are at most 2. So, if C is greater than or equal to 2, the penalty constant would not make a difference. On the other hand, by mistake if we change it to be less than 2, we will not get the solution, we may get a bad solution, but let us not go there. So, the classification by this SVM for any new f vector x is determined with the sign of f x, where mu I y I k x I x plus b star. Right. Let us first calculate b star to understand what this is. So, this is what mu I y I k x I x is k x 1 x, mu 1 is 1, y 1 is 1, k x 2 x, mu 2 is 1, y 2 is 1, minus 2 k x 3 x, because mu 3 is 2 and y 3 is minus 1, plus b star. Because I know x 1, x 2 and x 3, if you give me x, I can calculate all this. So, let us first calculate b star. You remember b star is given by this y j minus mu I y I k x I x j, for any j such that mu j is strictly greater than 0. In this case, all 3 mu j are strictly greater than 0. So, if I put j is equal to 1, what do I get? B star is y 1 is 1, minus the 3 terms here. First 2 terms will be positive, second term negative, because y 1, y 2 is positive, y 3 is negative. Mu 1 is 1, k x 1 is 4, that is 4, k x 2 x 1 is 0, and the other one is 1. I get a 2 from mu 3 and minus from, so that gives me minus 1. I do not have to choose j is equal to 1, any j will do. If I choose j is equal to 3, y 3 is minus 1. With respect to that, I once again put that in this, I get minus 1. Obviously, basically, if I solve your optimization problem correctly, no matter which j such that mu j is greater than 0 I choose, I should get the same b star. Matter of fact, this is one way I can check whether we have solved the optimization problem correctly. But when we do it numerically, this may not work. So, we may take b star to be the average of all b stars obtained with different j's. Okay. The minor issue, but anyway, so we have x 1, x 2, x 3 is this, and we know x k of x comma x prime is 1 plus x transpose x prime whole square. So, if I take x to be x 1 x 2, I know my function is k of x 1 x, k of x 2 plus k of x 2 x minus 2 k of x 3 x plus b star. What will be x 1 x? X 1 is this. So, this is 1 minus x 1 whole square. So, 1 minus x 1 whole square. X 2 is this. So, it will be 1 plus x 1 whole square. X 3 is this. So, x 3 transpose x is always 0. So, 2 into 1, b star is minus 1. So, 1 minus x 1 whole square plus 1 plus x 1 whole square will give me 2 x 1 square plus 2. That plus 2 will cancel with this minus 2, I get minus 1. So, my f x is 2 x 1 square minus 1, which means this SVM will assign class plus 1 to x, any given x 1 x 2, if 2 x 1 square is greater than 1 or x 1 is greater than root 2. This is exactly what we, as we said, the square of the first thing should be greater than some threshold. That is the SVM that is magically come out. We did nothing, we just chose a kernel function. Now, you may say, shouldn't the classifier be mod x 1 greater than half, right? So, that I put it exactly between the 0 and -1 or 0 and +1, right. That is what we are asking by maximizing margin. Well, we should understand that we are maximizing because we are using a kernel function, we are maximizing margin in the quadratic space, right, in the x1 square space. So, in the x1 square space, I want it between 0 and +1, that is at half. So, in the x1 space, it will be 1 by root 2, right, because we are maximizing margin in the transform space. Okay. So, the final SVM is intuitively very reasonable, and we solve exactly the same problem whether you are seeking a linear classifier or a non-linear classifier, right. So, this is a good example. So, we understand how to solve SVMs. Now, let us move on and look at the general case. This is what you want to solve, and we need a numerical method. As I said, due to the special structure, there are many efficient algorithms. We essentially look at only one structure here, what is called chunking. Chunking is simply that when you have a optimization of many variables, we do optimization of few variables at a time. Something that all of you might remember is what is called coordinate wise minimization. If you have a function of x1, x2, xn, we first keep x2 to xn fixed and minimize with respect to x1 as a one dimensional problem, then minimize with respect to x2, then minimize with respect to x3, and cyclically keep doing it. That is a simple idea of chunking. We optimize on only a few variables at a time, which allows the dimensionality of each optimization problem to be small, and at each iteration we randomly choose a subset of variables. Of course, we have to use some proper heuristics to decide how to choose. As long as all variables keep coming into the set being optimized again and again, essentially chunking works. This basic idea gave rise to the first specialized and very efficient algorithm for solving SVM, which is called SVM Lite. And then I can take I want to take chunking to the extreme level. SVM Lite takes 5 or 10 or 15 variables at a time, but I want to take chunking to the extreme level. I should ask what is the smallest chunk that I can optimize on. Because SVM has one equality constraint, I can optimize at most on 2 variables at a time. I can't change one variable keeping all the others fixed, because if I am at a feasible point and change only one variable, I go to an infeasible point, because there is a equality constraint. So, there is a special algorithm called sequential minimal optimization, which works on this principle of optimizing 2 variables at a time. Basically, this is very interesting algorithm, because if I keep rest of them fixed and I will say I optimize only on mu1, mu2, then by analytically manipulating the expression, I can calculate the optimum with respect to mu1, mu2, which means I do not have to do any numerical optimization at all. I spend all my time deciding which 2 variables, which 2 Lagrange multipliers I should do optimization next time, right. So, using a variety of heuristics, this algorithm does a very good job of solving the SVM optimization. Is a very, very efficient algorithm. Okay. So, I will just talk about this SMO and a couple of other issues in solving the SVM problem in the next class. Okay. Thank you.